If not, then I apologize for not being in the office hours yesterday, but I had a home emergency to take care of. So, okay, so let's go on with what we're going to talk about today then. So we've seen some parallel programming last week, and you're doing it now, but all of that was restricted to cores that can all see the same memory. So it's what we call shared memory programming. Today, we're going to look at how you would do it if the cores cannot see each other's memory. And that is the more typical situation for large-scale computations. Larger supercomputers are built out of smaller nodes. Each node has a number of cores and some memory. Those cores in one node can see all of the memory, but the different nodes cannot see each other's memory. There's no way for them to know what's going on in the other nodes, which is actually a good thing, but means that parallel programming has to be done differently. So you might need that if you need to scale up your number of cores. So if you need more cores because your computation is too slow, or if you need more memory. So each core, each node, I think each cluster has 64 gigabytes. Suppose that you need more than that. Then the only way to do that is to distribute your data, your application over more nodes. But that now means that the cores on those other nodes who are not seeing the memory of the first node. So shared memory programming has its troubles. It's limited to how big you can run. You can get race conditions, as we saw, and you can be limited in other ways as well. So what we're going to look at today and tomorrow, today and Thursday, and also next week, is to look at how you do this at scale. How you can really write a program that can run on any number of cores, whether they are on the same node or not. You could potentially even run this across like any network, although it might be slow. You want to run it on a network that is fairly fast. So what happens in those cases is that instead of having parallel tasks be threads within a program that are spawned through pragmas, each task is its own process. It's like running its own application. So all of these applications will have to be started and are just running, and then they each have their own memory, like processes do. And just as when you're running on your laptop and you're running your mail client and your web browser, they cannot see each other's data. That's on purpose. This is the same here. These processes cannot see each other's data. So it's the same if I run those on the same machine or on a different machine, they just can't see it. So how are they going to attack a problem at scale? How are they going to compute something that requires that knowledge of the rest of the system? And the way that is done almost always is by a library called message passing interface, or it's really a standard, and there's different libraries implementing that. So messages are going to get passed between the different processes. And I'll stress, we'll talk about processes now. They are no longer called threads, because that is restricted to this shared memory idea. What's nice about that is that once you've done it, you can scale up to any number of nodes, right? It's also harder to create race conditions. It's not impossible. Like if you're very smart, you can create that bug. But there's other bugs that come up now, like deadlock, and we'll look at those. So why would you even bother at this? Like Niagara has 40 cores per node. Surely that's enough for anybody to do their work on. It has 180 gigabytes of RAM or more. So do we really need to do that? Now, we might not always need to do that, but some people do. And in fact, right after this lecture at noon, we will start at SciNet a special event to do very large computations that require almost all of Niagara. So Niagara has 80,000 cores. We'll have a few groups that will run 20,000 or 40,000 or 80,000 or almost 80,000 core jobs. And to do that, you can't just run any application. As I said, even if it's OpenMP parallelized, it won't run on more than one node, which is 40 cores. So most of them rely on the MPI library. There's one in this bunch that uses CoRay Fortran. That's how to scope, because we're not doing Fortran here. But let me just say that that itself is very similar in many respects to MPI. It's nice, but it's similar, and it can be implemented with MPI. So by looking at MPI, we're still doing the same kind of stuff. So they achieve this by using MPI. And so that's why we're going to look at MPI. But even if you don't need to run on 80,000 cores, but just on 80, you'll need 2 nodes of Niagara, and you will need to use MPI. So for those of you that are Fortran programmers, feel free to look up how core array Fortran goes. But since we're using C++, we're doing plain old MPI. So let's look at MPI then. What is this thing? And so we're going to look at the basics. We're not going to start at 80,000 cores. We're going to start small, couple of processes, trying to overcome this barrier that we have different processes with their own memory, and they can't see it. There's no way to share that automatically. First of all, what is MPI? It's a standard. Oh, that's Michael asked, what are the projects that are part of Niagara at scale? So they will be, this is the first time we're doing this, so everything is slightly rushed. They would normally be announced first, but we will have a couple of user group meetings dedicated to showing the results. But they're all, for some reason, in the astrophysical realm. I guess those people were ready to run this big. There's a star simulation, there's some n-body simulations. So a lot of the techniques that we have heard of, like using our FFT for n-body dynamics, they're using that kind of stuff. Like all of the things that we've seen are part of their code. So that's the codes they're running now. But we had a call, people could propose, but the call was very short. So it's really the people that were ready to roll, so to speak. We're hoping in the future that there'll be a more wider distribution of projects. Okay, so MPI, getting back to MPI, it's a standard. So there's a standard committee or MPI forum that ratifies it. The first one was in 1994. Before that, there was no standard. So everybody that needed to do some sort of message passing, and back in that day, almost all of the machines were single core machines. So there was no other way to parallelize except doing some sort of message passing, but there was also no standard. So every new machine came with some sort of library that could do it, and you'd have to rewrite your code to suit that. So the advent of MPI was great, and now there was a standard. The standard evolves as it does. There are subversions. There's a version 2. We're now at version 3.1. That was ratified in 2015. But we'll mostly be using version 1 features anyway, because those are the basic things. The rest are somewhat advanced and sort of figure out details. They are working on a version 4. There's a draft out. So I'm expecting sometime this year there will be a version 4. But again, the differences in new versions get smaller and smaller as time goes on, because you've already covered the basics. So that's the standard. And then you need implementation. So there's 2 main implementations, OpenMPI and MPICH. They come out different national labs in the States, mostly not single ones necessarily, they're collaborations. But the nice thing of having different implementations is that the algorithms by which they support the standards are different. And so if something doesn't work in one standard or not very well, in one implementation, you can switch implementations. Your code does not have to change. So OpenMPI is kind of our default. So you can do module load GCC OpenMPI, and you'll have MPI. You can use it with the Intel compilers as well. MPICH we have in the form of a flavor of MPICH called Intel MPI. So it's I guess a commercial bundle of MPICH. There's like other versions, and MPICH is, for instance, very good for InfiniBand interconnects. But those are details that are implementation details. Sometimes they matter, but for us, it actually doesn't matter. we choose one or the other. If you have no preference, choose OpenMPI, because you got to have some sort of default. So we'll take OpenMPI and work with it. So once we've loaded those modules, we have MPI. But what do we really have? What do we get? We load it as if it's a module. Is it a library? Yes, it's a library. It's a library for message passing. So we do not have any so we do not have any language extensions here. The compiler doesn't know anything about MPI. Hold on 1 second. The compiler does not know about MPI. It knows about the library, and the library comes with a header, mpi.h, and everything goes through function calls, like a library does. So we have our int main, then this is just one process running. MPI will take care of making sure this runs n times, however many times n is, and then they communicate, these n copies communicate with MPI calls, MPI init, MPI com size, MPI com rank, MPI finalize. And we'll look exactly at what those do. Now, it's a library, so we know how to compile with a library. You use G++ -i for wherever the MPI.h header is, and then your code. And then if you're linking, you do -L and where the MPI library is, and -l MPI. But MPI is a rather complex library, so you need way more flags than your typical library. And for that reason, most MPI implementations come with a wrapper that add all of those -i and -l flags for you, and they're typically called MPI-CC, MPI-F90, and MPI-CXS. So it looks like they are MPI compilers. They're not. They are whatever other compiler you were using. So for our course, it will be G++. If we're using MPI-CXS, but they have added those flags that you need to successfully include the MPI header and to link to the MPI libraries and whatever other libraries that might be necessary. Okay, so we're going to use these compiler commands as if they're MPI compilers, but we're just really using G++ with a library. And so that's why the language hasn't changed. It's still C++. It's just convenient to do it that way. Okay, so here's a picture of what is going on. Suppose we had 4, and I'm calling them CPUs here, but I actually prefer cores better. So suppose we have 4 cores. They are each running their own application that is based on the same source code, but they're all running their own process. And because they're running their own process, they all have their own memory. Or they might be running different processes on different nodes. And then again, they have their own memory associated with each process. So that's the system. And then the only way we can figure out, say CPU1 can figure out what CPU2 has been doing is by these guys interchanging a message. Okay, so there's messages that have to be passed. Those messages will contain data. And so the data will go from whatever you specify to wherever you specify. The other thing that is, and this is a little tricky to get your head around, imagine that you are solving a puzzle with 3 friends. So there's 4 of you. And each of you get like about a quarter of the puzzle pieces. But the only way you're allowed to make the puzzle is to write little messages. And maybe with that message, you can attach some pieces of the puzzle and then pass it to your neighbor. But your neighbor has to know that the message is coming. That's the kind of complexity that we add here, because these are isolated nodes, isolated processes, right? So they don't know anything about each other. But it also means that there's no reason for one of the processes to set up everything for all the other ones. You will never say you wanted an array of 4. So your puzzle is really simple. It has 4 pieces. Each CPU, each friend should have 1 piece. There is no reason for one of the friends to start with all 4 and then distribute it. You just get 1 piece each. So this distributed way of thinking takes a second. Okay, so we'll see some examples, but it takes a second. It's very different from the OpenMP philosophy almost, where it looks like a single program in OpenMP and some parts are done in parallel. And so you would have all of your pieces in that program. Not so in MPI. You're going to completely distribute all of your data from the start, if you can. So what kind of messages can we pass? Well, we can go from one friend to the other, from one process to the other. So pairwise communications. There's also collective operations where you might have, say, CPU1 here is reading in the parameter file, say, and then it distributes that over all of them. That might be one way that you could imagine a collective operation. You might also want to sum up all of the numbers that it already has and give them to one process. Again, that's a collective operation. Okay, and then there's some efficient routines to help make messages, essentially. Pack data into messages. So the most basic case is that of a pairwise message. And in MPI, this is sort of the prototypical way that this will look. We are going from one core to another. We have to transfer some data. The data is of some type, MPI some type. We have a certain number of them. That part makes sense. So we have a sender, we have a receiver, we have a count, we have a type. In addition, in MPI, you can add a tag to this message. So this message goes in general over some sort of interconnect, some sort of network, and it will arrive, but maybe there's a lot of messages going on and you just want to make sure you're receiving the right kind of message. You can give it a tag that is checked. It's just an integer, it's just a whole number to check that you're receiving the right kind of message. Okay. Now, this has to be done, I said this already, actively. So if CPU1 is sending something and CPU2 doesn't have a receive statement somewhere, then this message will never be received and will be sort of be stuck in limbo forever. And depending on how you set it up, that might cause CPU1 to wait for the message to be sent forever. Okay, so you have to pair sends and receives. It is an active messaging. It's not a mailbox. It is actually, you have to be ready to receive this package. That's the model of this pairwise messaging. Okay, that's the tag. Okay, so MPI has a lot of functions in it. There's more than 200. The number of concepts is a lot smaller, luckily. A lot of these functions are variations of one another. And so we will get started with the basics, and the basics might well be all you need, about 10 or 12 function calls. And let's start with the very, very basic ones, the ones that I've listed on the right here. A function called MPI init, MPI comsize, MPI comrank, MPI send, MPI receive, and MPI finalize. They all start with MPI underscore. Then what follows is always a capital, and the rest has underscores and no more capitals. So you can never, so that's how you remember how the capitalization goes. But that is how it goes. Okay, here's our example again that we had before. This is our hello world in MPI. We're including the MPI header. And just to give it short, I use the std namespace. So I'm going to initialize MPI. At MPI init is kind of where the processes all come together. We will see that at some point these processes have to start, right? I'd say I want to run a 4-process MPI job. If I just run one of the applications, just whatever the compiler gave, it's one process. So there has to be a way to launch 4 of them at the same time, and there is. Once they're started, though, the codes of those 4 has to somehow find each other. On that same node, there could be many processes, right? And typically that's the case. So those 4 have to find and know that they are part of the same MPI group, MPI, whatever you want to call it. And what it is actually called is a communicator. So a group of MPI processes that can work together is called a communicator. And when you MPI in it, you create your communication group, your communicator. That communicator has a name. It's called MPI world. So it's a world of these 4 processes. And within that world, as I said, on the same node, there could be more processes, MPI processes, non-MPI processes. But this subset is its own world of 4 processes. In that world, every process gets a rank, gets a number from 0 to, in this case, 3, 0 to n-1, where n is the number of MPI processes that were started. You can also ask how many there are. So ideally, in an MPI process, you do not write a code specifically for a specific size. Sometimes you do, but usually you try not to. You could run the same code with 4 processes, 8 processes, 16, etc. All that you change is how you start them. And then MPI will tell the different processes what size they are by this MPI size command. So these two function calls, they get the rank and the size of your MPI processes, and then it prints them. After you're done with all of your MPI, typically in main, you have the MPI finalized. If you don't, some of these processes might not be done yet doing their stuff, and some are left dangling. You get funny error messages for no good reason. Excuse me. Michael asked if you could have more than one communicator. Yes. So you can take this communicator, this world communicator, and split it up in different parts and call those sub-communicators. And then you could have some of the processes doing one task and the others doing another task and communicate among themselves. And then there can be what's called an intercommunicator between those 2 communicators. So yes, you can make that as fancy as you want. There's, in addition to the MPI world, there's one other, there's, I guess, 2 other communicators defined. One is MPI self. You can only talk to yourself. It exists. And the world. And then I think there's one more, which is kind of a non-communicator. But yes, you can get fancy with the communicators, which is why you have to specify which communicator you mean every time you do an MPI call. So because you can have different communicators, even if you don't, even if MPI world is all you use, you will keep saying MPI world to all of the MPI communicators, MPI function calls, because these are functions. They don't know anything about your program, right? They're also, in case you hadn't noticed, they are C functions. So rather than having a function that just returns the rank and we assign it to int rank, we have to give a pointer to the integer that is supposed to hold the result. This is slightly annoying. In MPI, I think up to version 2, they had a C++ interface where you could say something like rank equals MPI rank or something like that. It was more object-oriented, but it didn't give any extra features. And so there was nobody that wanted to keep up updating a C++ version of this when you can just use the C version in C++. And the can is true. You can do that. But yeah, I find it unfortunate because I would have preferred a true C++ interface, but this is what we're dealing with. And I mean, I'm not the one that can tell a whole bunch of people to create a C++ interface just because I like it and not because I need it. Like I can understand that. So we're going to deal with this as a C library. And so that's why we have to pass pointers. But we've seen C libraries before, and we're kind of getting used to that, right? Okay, so that's our code. To compile it, so there's some code here in SciNet courses PHY1610 MPI. You can clone that, load your modules. And then to compile it, I'm using the MPI cxx command. Okay, so that is G++ with libraries that I don't have to specify, because the other flags all should look very familiar, right? They're exactly what you expect. Some optimization, C++ 14, where does output go, what's the input, and that's it. That's compiling it. It will create MPI hello world, and this is doing the compilation and linking in one step because there's a single file. You can do separate compilations just with -c and then link them again with MPI CXX, and it will work kind of just replacing G++ with MPI CXX. But now, suppose I want to run this. I want to run this MPI code. If I just ran MPI MPI hello world, which is what the executable is called, I get a single process, and it will do something, but it will not be parallel. I have to create 16 processes at once. So how do I do that? Well, I do that by the command MPI run. So MPI run also comes from the OpenMPI module, or so from the MPI implementation. Sometimes it's called MPI exec. In certain cases, when it's integrated with the scheduler, it might be called srun or slurm run. But MPI run tends to work in many cases, so kind of take that as its most common case. Funnily enough, in the standards, there's an MPI exec. But in many implementations, it's almost always MPI run. I'm not quite sure what happened there. So MPI run, and I have to specify how many of these I want to run at the same time. So I'm choosing 16. This is teach cluster. There's 16 cores, and then specify the application. So you prepend this here, and then what happens? Well, what happens then is that MPI run starts launching end processes, and depending on settings of the scheduler and host files and other things, these might run on the same node or on different nodes. In the ideal situation, and many situations are ideal, you've already specified how many nodes you want and how many processes on each node. MPI run just does it for you. So it basically starts these processes, possibly on different nodes, and then there's 4 of them, right? They all start at the same time. They don't really start from a single hello world. This is not a really good picture. They start from MPI run that then launches 4 of these MPI worlds. You usually run the same executable and therefore the same code. So here, that's what we're doing. It's almost as if we're running MPI hello world 16 times at the same time, with one added benefit. If we just ran it, say we opened 16 terminals and we typed MPI hello world in all of them 16 times at the same time, then we would get something similar, except those would not know, those different processes would not know that they're part of the same communicator. And so the MPI init would result in each process thinking they are a size 1 world. MPI run launches these things, but also tells them, usually by some environment variables, that they are part of a larger group, the communicator, and that they are and what their rank is in that communicator. The application doesn't know that yet until they call MPI init, but it has ways to retrieve that information, or the MPI library has ways to retrieve that through the MPI init call. Number of processes. Most of the time, you want the number of processes to be equal to the number of processors, so the number of cores that you're entitled to. If it's your own machine, that might be all the cores that are there. That's great. Other things will slow down, but that's what you can do. So you can try running this with more, but it'll just do the same thing as when we take too many threads in OpenMP. There'll be some swapping between different processes, and so they'll just basically slow down, and it's rather unproductive to do so. So we'll have if you try this, if you run this, and what I would suggest, because we're now running sort of at a considerable scale for a single node on the teach cluster, type debug job -n16. So you get 16 cores, and then you get a separate node for yourself where you can run these things, and you don't like step on each other's toes. These are very lightweight things, so in fact, you could probably do them on a login node, but get into the habit of grabbing a couple of cores to yourself to play with. Okay. So I'll show you what happens in a second, but you don't have to run an MPI program through MPI run. You can run any program. For instance, there's a program called hostname, which prints the name of the computer you're on. I can run that 4 times. And what I get is just, it launches those 4 applications and they run. They just don't call MPI init, so they don't know anything about MPI, but they all run at the same time and they'll print out the host name. And so what you'll see is 4 times the same host name. Okay. You can do it with the last too. Again, you can do it with anything, but there's not much point to it unless the application is an MPI application, because then it will call MPI init, it will ask its rank and its size, but it still runs the same code, right? So we need a way for those different processes to run different codes or different versions of the same code, or else they don't know what to do. So our Hello World program, when we print it, doesn't do exactly the same thing for each of them because it prints a different number. Right? So I've called them tasks here. So task 2 from 4, 1 from 4, 0 from 4, 3 from 4. If you're using OpenMPI, there's a nice flag you can add to mpirun, that's just tag output. That'll actually tell you which of the ranks you have. So I'm not quite sure what the when stands for in the front, but this is the rank again. So now you can sort of check that the different processes are indeed getting the right rank and doing the right thing. Okay. It's random, much as we saw in anything that's parallel. Outputs will appear to be in random order, but that's okay, or that should be okay. If it's not okay, that particular program was not parallelizable. You should take care of it differently. Okay, so that's how we compile something, how we run something, but we haven't communicated it yet, right? So while we could get a rank out of our process, out of the MPI library, and so we could print something differently, it's still not really attacking this, like the collaborating on attacking a single problem. So let's look at the basics again, and then try and find a way to do the actual message passing, which we haven't done yet. So the basic components here were including the library, our initialization, where the different processes learn about one another, and can, after that, they will be able to communicate. And then finalize, which closes the whole thing off, make sure nobody's left behind, everything went well. Now, formally, each of these calls actually returns an integer. The integer is an error code. Unfortunately, or maybe it's good, what happens in almost all implementations is that as soon as there is an error in one of the MPI calls, your program simply aborts. It crashes. It doesn't return that integer. It just says, that's it, something went wrong. This is horrible. Stop, everybody. And so when one process aborts, all of the other processes get a signal too to say, well, just get out of there. One of us has had an error, and so we're all stopping. There is ways to not do that, but that means that you kind of have to be able to understand what might have gone wrong and have a way programmed in to recover from that. And in many cases, when something does go wrong, it's true, your computation is just, it's wrong. Something's wrong, there's a bug. And so you should stop your process. You should go and look what went wrong, start up a parallel debugger like DDT, and check out what's going on, rather than just continuing on and hoping that things are okay. You should not hope, not in scientific computation. Okay, so after we've done init, we can ask our rank and our size. Where are we? How many of us are there? And that will tell us, the size will tell us how many ranks are possible. So rank 0 is the first one. The largest rank possible is rank -1. The one that this process has is in rank. Okay. Each process, again, separate memory, right? So process 0 has an int rank and a size, has a rank integer and a size integer. That's completely separate from all of the other ones. There's no need to make an array out of these for 4 of them, because then each of the processes would have an array of 4. They don't need it. They just need their own stuff. Okay. This is part of this distributed thinking that I was talking about. So now let's start communicating, right? So we have ranks in the MPI com world, and we can use those ranks to send things. We can say send to rank so and so. We can split up the communicators. I already talked about that, but we can have a MPI com worlds. We can make new communicators. We won't really see how this is done because it's kind of niche a little bit. But suppose you wanted one of your processes to be responsible for, say, I/O, like the writing to disk, and the other ones are just going to compute among themselves, and every now and then tell this I/O guy to do what it should do. So we have our com world, we have our rank size. There we go. Rank and size are extremely important, more so than in OpenMP, where we can ask for the thread num and the num threads. Yes, it's similar, but in OpenMP, there's ways to distribute work in a for loop without having to know how it's done, right? We don't have to know which iterations go to what thread. OpenMP takes care of that, and it can do that because it's a language extension. It can look into your code and basically change it to do that. MPI cannot do that. It's a library. It cannot look into your code. Those MPI CXX calls, they are not real compilers. They are just wrappers. It's still just G++, and G++ can't know what's going on in your other code. Okay, so the only way we can have a different rank do a different computation is to check the rank and from that deduce what it should do. But they have, like, each process has to do its own determination. Okay, so they can, every process will ask for its rank, and based on that rank, that process has to be able to deduce what its role is in the larger scheme of things. So that's how you have to write the code. You have to write the code from the perspective of a single process that's getting a rank and then decides, and then somehow figures out what is my job, my part of the computation that I have to do. What are the parts that I have to send to another process and back? So it's kind of low level, and it's something that is trickier. It's something that people don't particularly like. It would seem that there should be better ways to do it, but very few of those better ways to do it, to program it, to automate it, have really caught on. As I said, CoRay Fortran has a little bit, but it's still not very big in sort of high performance computing. And other languages have been invented to do this also, and they all have their nice features. And for one reason or another, MPI is still the go-to application or the go-to library to do distributed memory parallel programming, which is why we cover it here. Okay, so this has to be done. You have to get your rank as a process, and as a process, it has to figure out what is my role. It has to explicitly communicate. So not only does it have to figure out what is my role and what should I send to the other ranks at some point, it should also know what am I going to receive from the other ranks. Okay, so we'll have to have sending of messages, and we'll do that with ssend, and ssend stands for secure send, which makes sure that the package is actually en route, and receive, because you have to be able to receive it. So if there's no receive at the other end, the secure send will actually not stop. So it will wait until there's a process that is getting your message, getting your package. So those are the two, and we need a whole bunch of arguments to these. This is a library. The library doesn't know what is going on in your code, and it's a C library. So the first thing we have to say when we want to send something is, what do we want to send? And we can send something of any type, any number of elements, but since it's a library, it doesn't know what the type is of your variable. So you have to say what it is. If you're sending some doubles, you have to say MPI double as the type. If you're sending integers, MPI int, etc. We have to specify that because the library can figure out how big a double is. That's okay. But it doesn't know that what you're giving it as a data pointer is indeed a double. So what we're actually sending as a send pointer is a pointer to the message. So rather than sending the either a whole array, as in fact that could be a syntax, but it can't be. It's the pointer to the first element of your message. Then you have to say how many you're going to send. So that is in numbers of MPI type. That way, I don't have to do my own computation of 8 bytes times the number of doubles that I'm sending. I just say, send me number of doubles, MPI doubles. That specifies what I'm sending. And there's only one such function, MPI send. So this is going to be, I think, a void pointer, which works. That's OK. But that's also why the library cannot know what type you are. The other way around that would be to write different functions that can get different kinds of pointers. So we'd have an MPI send double, MPI send float. They decided that that's not a good idea. We're just creating one MPI send function, but this is how we specify what's sent. And then the next is what we send it to. So the destination, that's a rank, just a number. The tag that I said, so you choose a tag so the other side can check whether it's the right kind of message. And then the communicator, which in all of our examples is going to be MPI Comworld. Okay, so we're not going to do any fanciness with the communicators. It's all going to be MPI Comworld, but we have to specify it anyway. Okay. The receive, on the other hand, will have to have a buffer, an array ready to receive this data. It can't allocate the array for us. So if we put it in an array and it wasn't allocated yet, then that will call segmentation faults because we're writing into memory that we have not allocated yet. So we can say where our ready buffer for receiving this data is, how many elements would fit in it. So that at least is good. You don't know how many elements are going to get sent on the other side, but you can limit how much you are willing to receive at most. It could be less, that's okay, but at most this many of what type. And then where is it going to come from? What is the tag that I expect? What is a communicator? And then there's an additional argument, an MPI status, which gets filled with things like how many numbers, how many data points did I actually receive, and some other things. You can get some extra information out of that. Okay, so one process does send, the other process does receive. They're not both doing that. One has to send, one has to receive, right? Yes. Okay. So as I already said, this is the C interface. There's a photo interface which very closely follows this same interface. There's a slight difference, but you can look that up. We are using the C interface. That's why we have pointers. So send pointer, receive pointer. Typically, you'll do things like data, .data if you have an R array, or explicitly take the address of array element 0. Things like that will go into your send pointer. Okay. Okay. So here's a first example to see how we would go from sending a message from one to the other. So this is supposed to be a MPI process or an MPI application that expects to be run as two processes, and one process, the one that with rank 0, will send a message, which is a single double. Its value set here to 111, so 111, to the right. In other words, to rank 1, whereas rank 1 will be receiving that double and then saying what it received. Okay. This kind of explicitness is something you should generally avoid in MPI programming because it's very explicit and only works for 2 ranks, all these if statements, but it does explain a little bit what's going on. So when we're compiling this and then running this, we will get, we will see if we run it with 2 processes, send 111 from 0 and received 111 from 1. So what happens, let's see if we can, is that this code gets compiled to the same executable. It's run twice, right, at the same time. But one of those processes that is run after MPI init and comRank will get a rank equal to 0, and the other one will get a rank equal to 1. And the rank 0 one will only execute the part that's in the if rank equals 0. Right. So it's really it's almost 2 separate programs. That either execute this, the other one is executing that. And so there's a send, there's a receive. They are what is called paired. So for every send, there is a matching receive, and everything is fine. Michael asks, if a process expects to receive the message, but the sender hasn't gotten there yet, will it just be idle until it receives the message? And the answer is yes. It will. So this receive will wait. Is what's called a blocking MPI call. It will wait until something is there to be received. Yes. Same with send. If send is sending but receive is not ready, so rank 1 is not ready to receive, it will wait until it's ready to receive. So it synchronizes at those points, but it's hard to see in the code, but it synchronizes sort of in the general MPI world. Okay, so let's do one more example, and then we'll stop for today because I have to get going on the Niagara at scale. Let's see how we can send a message to the right. But now, and not just one, but every process sends its message to the right. That's one typical communication pattern. There's a few special things that happen here because there's nothing to the right of 2. And so one of the things we can do as our special destination source is to use a thing called MPI proc null. So we can do a send, but send it to nowhere. And now it's no longer a blocking call. It just says, okay, if this is null, that is fine. So each of these processes will run the same code. Process 1 will receive something from the left and send something to the right. Fine. But process 0 will also receive something from the left, but it will receive it from MPI proc null. Likewise, we can use, but we're not going to use that here, MPI any source, which means we don't care where we get our message from. Just whatever message is incoming, regardless of where it's coming from, get it. And there are cases where that is a useful special thing. I don't have a. This is not the code. Yes, so this is the code for that. I don't know where the deadlock was in the middle there. So we've got our rank size. Now we have to figure out what is left of us and right of us. And it is useful often to put those in variables. So I know my rank. What is to the left to me is rank -1. Except if there's nothing to the left. And then I just set my left to MPI proc null. By doing that, I can send things to the left or send it to the fake left with the same code. So the code here that's sending things to the left, or actually to the right, yes, is doing that. But for some process, the one that's at the end, it actually doesn't do anything, and that is fine. That means I can have a simpler code. Same for the right. I'm sending some messages and receiving them. So there's a send and a receive on each of them. That's right. Some of these don't do anything because there's no process on either end, and that is encoded here, and that's working. So I'm going to stop here, and we'll have 3 whole lectures in total to spend on MPI. But that's going to be enough for today. It's a very different mindset, so it'll take a little while to sink in that you don't have one program running. You have several running that have distributed their load. Any questions? If there's no questions, we'll wrap it up, I guess. Okay, see you all on Thursday, or maybe tomorrow on the office hours.